There's something humbling about looking up at the night sky, a quiet reminder that we're part of something far grander than our everyday lives. Each star, each distant galaxy, is more than just a pinprick of light. It's a piece of an intricate cosmic puzzle, governed by unseen forces working in perfect harmony. Think about it. The universe doesn't operate by chance. Behind the scenes, there's a symphony of mechanisms so precise, so beautifully orchestrated, that they shape everything from the tiniest particles to the vastest structures in space. And today, we're pulling back the curtain on 25 of these hidden wonders, the invisible architects of reality itself. What if I told you that dark matter, an elusive substance we can't even see, is the glue holding galaxies together, or that quantum entanglement, a phenomenon Einstein called spooky action at a distance, allows particles to communicate instantaneously across unimaginable distances? These aren't just abstract ideas, they're the gears turning behind the scenes, crafting the universe as we know it. From the way gravity sculpts the cosmos to the mysterious energy accelerating its expansion, every mechanism we'll explore is a thread in the tapestry of existence. And here's the most fascinating part. Understanding these forces doesn't just satisfy curiosity, it rewires how we see the world. Suddenly, chaos reveals its hidden order, and the universe transforms from a random void into a masterpiece of precision. This isn't just a journey through space and time, it's an invitation to witness the hidden blueprint of reality. By the time we're done, you'll see the night sky differently, not as a scattering of distant lights, but as a living, breathing network of interconnected marvels. So let's begin. Together, we'll uncover the cosmic mechanisms that power existence, one astonishing revelation at a time. The universe has been waiting to share its secrets. Are you ready to listen? Take a moment to picture the largest structure in existence, one so vast it makes galaxies look like specks of dust. This is the cosmic web, an intricate network of invisible threads stretching across the universe, built entirely by dark matter. Though we can't see it directly, its presence is undeniable. Every galaxy cluster, every swirling nebula, is anchored to this hidden architecture like beads on a string. The reason: dark matter's gravity acts as the ultimate cosmic glue, pulling ordinary matter into its gravitational embrace over billions of years. Here's how it works. Imagine tossing a handful of sand onto a spiderweb. The grains don't just fall through, they catch where the strands intersect, clustering at certain points. That's exactly what happens in space. Dark matter forms these colossal filaments, and where they cross, galaxies gather like cities at the junction of invisible highways. Scientists uncovered this blueprint by studying how light bends around massive objects, revealing the web's ghostly outline. Even more astonishing, the cosmic web isn't static. It's alive with motion, constantly growing and reshaping itself in an endless dance of gravity. Without this unseen framework, the universe would be unrecognizable. Stars would drift aimlessly, galaxies would never have formed, and life as we know it wouldn't exist. It's a humbling thought. The very foundation of reality depends on something we've yet to fully understand. Yet every time astronomers peer deeper into the cosmos, they find new evidence of dark matter's handiwork, proof that the universe's greatest mysteries are also its most essential builders. Now let's shrink our perspective way down to a realm where reality itself seems to flicker. In the seemingly empty void of space, there's a hidden frenzy of activity. Particles and antiparticles pop into existence for fleeting moments before vanishing again, like bubbles in a cosmic soda. These are quantum fluctuations, And they're not just microscopic curiosities, they're the very seeds from which galaxies, stars, and even we ourselves grew. Picture the early universe a fraction of a second after the Big Bang. Space wasn't smooth and uniform. It was a roiling sea of these tiny, unpredictable fluctuations. Then came inflation, the universe's explosive growth spurt, stretching those microscopic ripples across the cosmos. What started as quantum whispers became the gravitational scaffolding for everything we see today. It's as if the universe took a handful of quantum confetti and blew it up to galactic proportions. Randomness at the smallest scale, transformed into the grand design of the cosmos. Here's the astonishing part. Without these fluctuations, space would be a vast, featureless desert. No stars, no planets, no swirling nebulae, just an endless, unchanging expanse. The same quantum mechanics that govern particles in a lab also dictated the fate of the universe. Those fleeting particles weren't just noise, they were the first brushstrokes on the canvas of reality. Scientists have even detected the faint echoes of these fluctuations in the cosmic microwave background, the afterglow of the Big Bang, like finding the fingerprints of creation itself. So next time you gaze at the night sky, remember, the majesty of the cosmos began with the tiniest tremors in the fabric of nothingness. What seems like chaos at one scale becomes the blueprint for beauty at another. The universe didn't just unfold, it hummed into existence, one quantum fluctuation at a time. At the heart of nearly every galaxy, including our own Milky Way, lurks an invisible titan, a supermassive black hole with gravity so strong, not even light can escape. But here's the twist, these cosmic behemoths aren't just engines of destruction. They're master regulators, acting like galactic thermostats to maintain balance across the universe. Imagine a furnace that doesn't just burn fuel but precisely controls the temperature of an entire city. That's the role black holes play in their galaxies, only instead of heat, they manage the very fabric of star formation itself. When a supermassive black hole feasts on surrounding gas and dust, it doesn't consume quietly. It erupts, shooting out colossal jets of energy at nearly the speed of light. These jets act like cosmic blowtorches, heating the surrounding gas cloud so intensely that they can no longer collapse to form new stars. It's a self-correcting mechanism, a feedback loop where the black hole's appetite directly controls its galaxy's growth. The more material it devours, the more energy it blasts back, preventing runaway star formation that could otherwise exhaust a galaxy's resources too quickly. This delicate balance explains one of astronomy's great mysteries: why some galaxies abruptly stop producing stars billions of years earlier than expected. Without black holes acting as these cosmic pressure valves, galaxies might grow uncontrollably, burning through their gas reserves in a frenzy of star birth. Instead, the universe maintains equilibrium, chaos, and creation locked in an eternal dance. Even more fascinating, the same process might explain why we don't see galaxies 1,000 times larger than our own. Black holes don't just shape their homes, they enforce cosmic zoning laws, ensuring no single structure dominates the universe. Evidence for this intricate system is written across the sky. Astronomers have observed galaxies where black hole jets have carved vast bubbles in surrounding gas, leaving behind eerie, starless voids. Other galaxies show shockwaves rippling through their cores, like echoes of a black hole's last meal. These aren't random acts of violence, they're signatures of a finely tuned mechanism, one that's been operating since the first galaxies formed. So the next time you hear about black holes as destructive forces, remember, they're also the universe's way of keeping things in check. Without them, galaxies might burn too bright and fade too fast. In the grand design of existence, even the most terrifying phenomena serve a purpose, turning chaos into balance, destruction into renewal. The universe, it seems, has a way of regulating itself, with black holes as its unlikely custodians. Every second, trillions of ghostly particles stream through your body without a trace. Neutrinos, the universe's most elusive travelers. Nearly massless and almost invisible to matter, they slip through planets like sunlight through glass. But here's the twist: these particles are cosmic shape-shifters. As they race across the universe at near light speed, they don't stay the same. They oscillate, morphing between three distinct identities: electron, muon, and tau neutrinos, like a magician cycling through disguises mid-performance. This isn't just a quirky subatomic trick. Neutrino oscillations shattered physicists' expectations, revealing that these particles have mass, something the standard model of particle physics never predicted. Think of it like discovering a hidden rule in a game everyone thought they understood. When scientists first detected neutrinos from the sun, they found far fewer than theories suggested. The reason: the neutrinos hadn't vanished, they'd simply changed form along their journey, like a chameleon blending into new surroundings. But the implications stretch far beyond textbooks. Neutrino oscillations play a starring role in some of the universe's most violent events. When a massive star explodes as a supernova, 99% of its energy bursts out in a torrent of these shape-shifting particles. Their behavior determines how the explosion unfolds, how elements like gold and uranium are forged, and even how the shockwave ripples outward. It's as if these tiny particles hold the blueprint for stellar death, a silent conductor orchestrating the chaos. Even more mind-bending, neutrinos from the early universe still wash over us today, unchanged after billions of years. By studying their oscillations, we're essentially decoding messages from the cosmic dawn. They're time travelers, carrying secrets about conditions moments after the Big Bang, when the universe was a seething soup of primordial energy. So the next time you feel nothing as neutrinos pass through your hand, remember, you're being touched by particles that defy the laws we thought governed reality. They're proof that the universe still has cards up its sleeve, whispering through these ghostly alchemists that there's more to existence than we've yet imagined. Consider a balloon inflating so rapidly that every tiny crease on its surface vanishes in an instant. That's cosmic inflation, the universe's own breathtaking growth spurt, where space itself stretched faster than light in the first fraction of a second after the Big Bang. This wasn't just expansion, it was a transformation so radical it set the blueprint for everything that followed. In less time than it takes to blink, the universe grew from smaller than an atom to the size of a grapefruit, smoothing out wrinkles in spacetime like an iron-flattening cosmic fabric. Why does this matter? Picture tossing confetti into the air. Without inflation, you'd expect clumps and gaps, some areas dense with paper, others eerily empty. Yet when we look at the cosmos, the distribution of matter is eerily uniform, no matter which direction we observe. Inflation explains this mystery. It stretched the universe so thoroughly that any initial irregularities were ironed out, leaving behind the smooth, homogeneous canvas we see today. But here's the catch: the process wasn't perfect. Tiny quantum fluctuations, those microscopic ripples we discussed earlier, were stretched along with everything else. These imperfections became the seeds for galaxies, the subtle variations in density that gravity would later sculpt into stars and planets. The evidence for inflation is etched into the oldest light we can detect, the cosmic microwave background. This afterglow of the Big Bang shows faint temperature variations, a fingerprint of those primordial quantum tremors magnified to cosmic scales. It's as if we're looking at a snapshot of the universe's first moments, frozen in time. Without inflation, these patterns wouldn't exist, and neither would the structures they spawned. But inflation's greatest gift might be survival. In those early moments, the universe teetered on a knife's edge. Without exponential expansion, gravity could have pulled everything back into a catastrophic collapse, a big crunch before stars ever had a chance to ignite. Instead, inflation flung matter apart with such force that the cosmos had room to evolve, cool, and eventually give rise to us. It's a humbling thought. The very existence of galaxies, planets, and life might hinge on a fleeting event that lasted less than a trillionth of a second. Some theories even suggest inflation didn't happen just once. The idea of eternal inflation proposes that our universe might be one bubble in a frothing multiverse, where new regions of space are constantly undergoing their own runaway expansion. If true, it means inflation isn't just a historical footnote. It could still be happening beyond the edges of our observable universe, birthing new realities with their own unique laws of physics. So the next time you marvel at the night sky's vastness, remember, its grandeur traces back to an epoch of unimaginable speed and scale. Cosmic inflation didn't just shape the universe, it made the universe possible, turning a fleeting moment into the foundation for all of existence. And its echoes still resonate today, written in the patterns of galaxies and the whispers of ancient light. There's a strange connection in the quantum world that defies everything we know about space and time. Two particles can become entangled, bound together in such an intimate dance that changing one instantly alters the other, no matter how far apart they are. Picture tossing a pair of gloves into opposite ends of the universe. Open one to find a left hand, and its partner instantly becomes a right hand, even if it's billions of light years away. Einstein famously dismissed this as spooky action at a distance, refusing to believe information could travel faster than light. Yet decades of experiments confirm entanglement is real, and its implications rewrite the rules of reality. How does it work? When particles become entangled, they lose their individual identities, merging into a single quantum state. Measure 1, and its twin snaps into a corresponding state faster than a heartbeat. This isn't just theoretical. Scientists have sent entangled photons through fiber optic cables across cities, even beamed them to satellites in orbit, and the effect holds. Distance seems irrelevant, as if the universe has an invisible hotline connecting these particles behind the scenes. The real magic lies in what entanglement suggests about the nature of reality. Some physicists propose it's not just a quirk of tiny particles, but a fundamental feature of spacetime itself. Imagine the cosmos as a vast network where everything is subtly linked through these quantum threads. Black holes might use entanglement to preserve information, and some theories suggest spacetime itself could emerge from a web of entangled quantum bits, like a 3D hologram projected from deeper, interconnected layers of reality. Then there's the technological revolution it could unlock. Quantum computers rely on entangled qubits to perform calculations exponentially faster than classical machines. Encryption could become unbreakable, medicines could be designed atom by atom, and AI might leap forward by harnessing this eerie synchronization. Even now, labs are racing to build quantum networks where information teleports across distances, not through wires but via entangled particles. Yet for all its promise, entanglement remains deeply mysterious. Why does the universe allow such intimate connections that bypass the speed of light? Could it be a clue that separateness is an illusion, that at some fundamental level everything is interwoven? Every experiment peels back another layer, revealing a cosmos far stranger and more connected than we ever imagined. The spookiness Einstein feared might just be the universe's way of showing us how little we truly understand. Long before the first stars flickered to life, the universe was filled with a roaring ocean of sound waves crashing through a superheated plasma so dense light couldn't travel an inch without being scattered. These weren't ordinary sound waves. They were pressure ripples unleashed by the Big Bang itself, racing outward at half the speed of light. And though that primordial symphony faded billions of years ago, its echoes still shape the cosmos today. Meet Baryon acoustic oscillations, the universe's fossilized heartbeat, etched into the arrangement of galaxies across the night sky. Here's how it happened. In the first few 100,000 years after the Big Bang, the universe was a scorching soup of particles, so hot that atoms couldn't form. Photons and matter were locked in a violent tug of war, with gravity trying to pull particles together while radiation pressure pushed them apart. This created colossal sound waves, regions where matter piled up like the crest of a wave, followed by troughs where it thinned out. The waves traveled outward until the universe cooled enough for atoms to form, freezing the patterns in place like footprints in hardening concrete. Today, those frozen waves reveal themselves in a startling pattern. Galaxies are slightly more likely to be separated by about 500 million light-years, the exact distance those ancient sound waves could travel before the cosmos cooled. It's as if the universe stamped itself with a cosmic ruler, a scale so vast it stretches across billions of light-years. Astronomers use this imprint like a measuring tape to track how dark energy stretches space-time itself. Every time they map millions of galaxies and find that recurring 500 million light-year spacing, they're glimpsing the ghostly aftermath of the universe's first and loudest sound. But the real magic lies in what these oscillations tell us about dark energy, the mysterious force accelerating the universe's expansion. By comparing the ancient BAO ruler to modern galaxy distributions, scientists can measure how much dark energy has stretched the fabric of space over time. It's like watching a shadow grow longer and debasing the position of the sun. The tighter the galaxy clusters cling to that original half-billion light-year spacing, the more we learn about dark energy's grip on cosmic evolution. What's astonishing is how precise this cosmic fingerprint remains after nearly 14 billion years. Even as galaxies collide, clusters merge, and supernova explode, that primordial spacing persists, a testament to the universe's perfect memory. The same forces that once made the cosmos ring like a bell now help us unravel its greatest mysteries. And with next-generation telescopes like the Vera Rubin Observatory mapping billions of galaxies, we're on the verge of hearing those echoes clearer than ever, tuning into a song that began before time had meaning. So the next time you see a galaxy through a telescope, remember, its place in the cosmos isn't random. It's part of an ancient rhythm, a vibration set in motion when reality was young. The universe didn't just expand, it sang itself into existence, and we're only now learning to listen. We take the laws of physics as fixed, unshakable truths. Gravity pulls, light travels at a constant speed, particles have mass. But what if these rules aren't the universe's final draft? Lurking in the fabric of reality is a theoretical doomsday scenario called vacuum decay, where the very ground beneath our feet, not the Earth, but the quantum fields that define existence, could suddenly shift, rewriting physics in an instant. At the heart of this unsettling idea is the Higgs field, an invisible energy blanket that permeates all of space. It's what gives particles their mass, like a cosmic molasses slowing them down. For decades, we've assumed this field sits comfortably in its lowest energy state, a stable valley in the landscape of quantum possibilities. But some theories suggest it might only be perched on a ledge, with a far deeper valley hidden below. If true, a single quantum event, a random fluctuation, a high-energy collision, could nudge the Higgs field off its ledge, triggering a catastrophic phase transition. Imagine a bubble forming in the depths of space where the laws of physics inside are fundamentally different. This bubble wouldn't just sit there, it would expand at the speed of light, erasing the old universe as it grows. Atoms would unravel, forces would reconfigure, and the building blocks of reality as we know them would cease to exist. There'd be no warning, no time to react. One moment, the universe operates by familiar rules. The next, an unstoppable wall of new physics sweeps through, rewriting everything in its path. The good news. If the Higgs field is metastable, as some models suggest, it could take longer than the current age of the universe for such a bubble to form spontaneously. The bad news, we can't rule it out entirely. Particle colliders like the Large Hadron Collider might even theoretically create the conditions for a bubble if they reach energies high enough to destabilize the field. Though the odds are astronomically low, the mere possibility forces us to confront an unsettling truth. The universe's laws might not be permanent. They could be a local custom, a temporary configuration in a much vaster cosmic tapestry. Yet there's a strange beauty in this fragility. Vacuum decay isn't just a doomsday scenario, it's a reminder that reality is dynamic, capable of reinventing itself. Some theories even suggest our universe might have been born this way, a bubble of new physics in an older, alien cosmos. If so, the cycle could be eternal, universes rewriting themselves, each with its own unique rules, its own fleeting moment of stability. So while we don't need to lose sleep over vacuum decay, it does something profound. It humbles us. The constants we rely on, the equations we treat as gospel, might just be a temporary arrangement, a cosmic coincidence that's allowed us to exist. And that realization changes how we see the universe, not as a fixed stage, but as a story still being written, one quantum fluctuation at a time. Magnets usually come in pairs. A north without a south is as unthinkable as a smile without a mouth. Yet for nearly a century, physicists have hunted for the impossible, magnetic monopoles, particles carrying just one pole, wandering through the cosmos like solitary ghosts. Their existence was first predicted by quantum theory, which suggested these exotic relics should be as common as stars. But the universe seems to have hidden them away, leaving behind one of physics' most tantalizing missing pieces mysteries. The story begins with the early universe, when forces we now consider separate, electromagnetism and the weak and strong nuclear forces, were unified as one. In those searing conditions, theory says defects should have formed in spacetime's fabric, like cracks in ice as it freezes. These defects would manifest as monopoles, cosmic knots of pure magnetism. But here's the puzzle. If the math is correct, there should be enough monopoles today to outnumber atoms. The fact that we haven't found a single one suggests something extraordinary happened to wipe them out. That's where cosmic inflation, the universe's explosive early growth spurt, comes in. By stretching spacetime exponentially, inflation could have diluted monopoles to near invisibility, scattering them so thinly that finding one would be like spotting a single grain of sand in a desert the size of the observable universe. Think of it as blowing up a balloon with a few specks of paint inside. As it inflates, those specks become vanishingly small against the expanding surface. Yet the hunt continues because discovering even one monopole would rewrite physics. For starters, it would prove that electric and magnetic forces aren't fundamentally different, just two sides of the same coin, unified under extreme conditions. It could also explain why charge comes in fixed amounts, as monopoles would require electric charge to be quantized, like pixels on a screen. Some grand unified theories even suggest monopoles could catalyze proton decay, turning ordinary matter into pure energy in a flash. So where might these cosmic fugitives hide? Some theories point to the cores of neutron stars, where unimaginable pressures could squeeze matter into exotic forms. Others speculate they're trapped in cosmic strings, filaments of energy left over from the Big Bang, floating between galaxies. There's even a chance they're buried deep underground, having fallen to Earth over billions of years. Experiments like MOEDL at the Large Hadron Collider are designed to catch them, using detectors sensitive to the telltale trails monopoles would leave. What's fascinating is how their absence shapes our understanding of the universe. The fact that we don't see monopoles is paradoxically some of the strongest evidence for inflation, a cosmic eraser that wiped the slate clean. Yet if we ever do find one, it won't just fill a gap in our theories. It'll open a door to a deeper layer of reality, where the symmetries of nature reveal themselves in ways we've only dreamed of. Until then, monopoles remain the universe's most elusive might-have-beens, whispering secrets from a time when the cosmos was new. Imagine peeling back the layers of reality only to find a cosmic sleight of hand, a universe where 3 dimensions are nothing more than an elaborate illusion. This is the holographic principle, a mind-bending idea born from the study of black holes that suggests everything we see, touch, and experience might be encoded on a distant, 2-dimensional surface. Think of it like a movie projected onto a screen. The images appear to have depth, but every detail is actually stored in flat, pixelated data. Only in this case, the screen is the edge of the observable universe, and the movie is existence itself. The story starts with black holes, those cosmic paradoxes where gravity is so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, or its hidden information content, isn't proportional to its volume, as you'd expect, but to the area of its event horizon. It's as if all the data about what fell into the black hole was compressed and painted onto its surface, like a mural capturing an entire library's worth of books in a single fresco. This hinted at something profound, that the universe might not store information in 3 dimensions at all. Instead, it could be a hologram with every particle, every force, every whisper of energy in our 3D world traced back to flickering bits on a vast, flat canvas. But how could this possibly work? Picture the pixels on your phone screen. Up close, you see individual dots, but step back and they blend into a seamless image. The holographic principle suggests space-time operates similarly, with tiny, indivisible pixels of reality at the Planck scale, distances so small that measuring them would require probes with more energy than the entire universe contains. These aren't pixels of light, though. They're bits of quantum information woven into the fabric of space-time itself. And just as a hologram can reconstruct a 3D object from 2D interference patterns, the universe might reconstruct our perceived reality from data etched onto its boundary. Evidence for this audacious idea comes from an unexpected place, the mathematics of string theory. When physicists grapple with equations describing higher dimensional spaces, they often find equivalent, simpler versions that play out in fewer dimensions, like translating a complex novel into a different language without losing its meaning. This mathematical duality suggests our 3D universe could indeed have a 2D counterpart, with both descriptions equally valid. Even more compelling, the principle resolves one of physics' great paradoxes: how to reconcile Einstein's smooth, continuous spacetime with quantum mechanics' grainy, probabilistic nature. If spacetime is fundamentally pixelated, the two theories might finally shake hands. Yet the holographic principle isn't just about physics, it reshapes how we see reality. If true, it means the solidity of the world around us is a kind of cosmic augmented reality, a projection so flawless we'd never notice the seams. It raises haunting questions. Are we the hologram or the observers decoding it? Could the universe be a simulation running on some unfathomable surface? And if information is the true currency of reality, what does that say about consciousness itself? While we're far from proving the universe is a hologram, experiments are chipping away at the mystery. Fermilab's holometer, for instance, hunts for spacetime's pixelation by looking for quantum jitter in laser beams, tiny vibrations that might betray the underlying grid of reality. So far, the cosmos keeps its secrets, but every null result narrows the possibilities. What's undeniable is how the holographic principle turns intuition inside out. It tells us that the universe's deepest truths might not lie in the vastness of space, but on its shimmering edges, like a shadow theater where the real story unfolds not in the puppets, but in the light behind them. Whether metaphor or fundamental law, it's a reminder that reality is stranger than we dream, and the cosmos still has cards left to play. Deep in the cosmic shadows, an invisible contender for dark matter's crown waits to be discovered, not a particle of force or fury, but one of quiet, almost ghostly subtlety. Actions theorized in the 1970s to solve a puzzle in quantum physics might be hiding in plain sight, weaving through the universe like silent spectators. Unlike their flashier dark matter candidates, actions wouldn't announce themselves with bursts of energy or violent collisions. Instead, they'd reveal their presence through the faintest of cosmic whispers, bending starlight in ways we're only beginning to understand. The story starts with neutrons, those unassuming building blocks of atomic nuclei. When physicists studied them in intense magnetic fields, they noticed something odd. Neutrons refused to split their positive and negative charges the way other particles did. This strong CP problem hinted at a missing piece in our quantum rulebook, a symmetry so perfect it demanded an explanation. Enter actions. Hypothetical particles propose to restore balance by quietly cancelling out neutron irregularities. But here's the twist: these particles, born to fix a quantum hiccup, might also be the very stuff dark matter is made of. Imagine a universe filled with actions, each billions of times lighter than an electron, drifting like a fine mist through galaxies. Their collective gravity could explain why galaxies spin faster than visible matter allows, or why light bends around cosmic voids. Unlike other dark matter candidates, actions wouldn't clump densely around black holes or galaxy cores. Instead, they'd form vast, diffuse clouds, subtly warping spacetime on scales we're only now learning to measure. Detecting them is like tuning a radio to a station buried under static. Actions, when exposed to strong magnetic fields, might occasionally convert into photons, extremely faint radio waves with precise frequencies. Experiments like ADMCS use superconducting cavities cooled to near absolute zero, acting as cosmic ears straining for these elusive signals. It's needle in a haystack science, where success could come down to distinguishing an action's whisper from the background hum of the universe. Yet the payoff would be staggering. Confirming actions wouldn't just unmask dark matter, it'd open a window into quantum symmetries forged moments after the Big Bang. These particles might even hold clues about inflation, their ultra-low mass tying them to that explosive expansion. And if they're out there, they're rewriting the rules of particle physics in real time, proving that sometimes the universe hides its greatest secrets not in fireworks, but in silence. So while actions remain hypothetical, their potential is anything but. They remind us that the cosmos often speaks in riddles, and the answers we seek might be hiding in the quietest corners of reality, waiting for the right moment to step into the light. The Milky Way isn't drifting through space alone. It's caught in a river of galaxies, all flowing toward something invisible. This is the Great Attractor, a gravitational anomaly so powerful it pulls entire clusters of stars toward it at over 2 million kilometers per hour. Yet for decades, its true identity remained hidden, obscured by the thick dust and stars of our own galaxy's central bulge. It's as if the universe hung a cosmic curtain across the stage, keeping its greatest spectacle just out of view. What makes this mystery even more compelling is scale. The Great Attractor isn't just tugging on a few nearby galaxies, it's influencing over 500,000 of them across a region spanning hundreds of millions of light years. Picture a whirlpool in a cosmic river with spiral galaxies like ours caught in its current. Early observations in the 1970s revealed this strange motion, showing that galaxies in our local supercluster weren't just expanding with the universe. They were veering off course, drawn toward some unseen mass. For years, astronomers could only guess at what lay behind the Milky Way's dusty veil. Some speculated it was a supercluster of galaxies so dense it warped space-time like a bowling ball on a trampoline. Others wondered if it might be something more exotic, a concentration of dark matter so vast it defied explanation, or even a remnant of primordial forces from the universe's infancy. The turning point came with infrared and radio telescopes, which pierced through the obscuring dust to reveal the Norma Cluster, a massive gathering of galaxies at the heart of the Great Attractor's pull. But here's the twist: even this colossal structure isn't heavy enough to account for the observed motion. That discrepancy led to an even bigger revelation. Beyond the Great Attractor lies something far more immense, the Shapley supercluster, the largest known concentration of matter in the observable universe. This titanic structure, containing tens of thousands of galaxies, might be the true puppet master, its gravity amplifying the Great Attractor's pull like an echo in a canyon. Yet the math still doesn't quite add up, leaving room for the possibility that something even stranger lurks in the cosmic shadows. What's humbling is how this mystery reframes our place in the cosmos. We're not stationary observers in a static universe. We're passengers on a galactic conveyor belt, swept along by forces we've only begun to map. The Great Attractor reminds us that even as we peer deeper into space, the universe keeps its grandest designs just out of sight, urging us to look further, dig deeper, and stay curious. After all, the greatest discoveries often lie not in what we can see, but in what pulls us toward the unknown. There's a moment in the cosmic dance when two neutron stars, stellar corpses so dense a teaspoon would weigh 1 billion tons, finally spiral into each other's embrace. The collision is anything but quiet. In less than a second, these ultra-compact remnants unleash more energy than our sun will produce in its entire lifetime, rippling space-time with gravitational waves and lighting up the cosmos with a blaze of gamma rays. But the real magic happens in the aftermath, as the cataclysm becomes a cosmic alchemy lab, forging elements so heavy they can't be made any other way. This is how gold is born, not in the fiery hearts of stars, but in the violent wreckage of their deaths. When neutron stars merge, the extreme conditions, temperatures exceeding 1 trillion degrees, pressures that crush atomic nuclei like grapes, create a perfect crucible for rapid neutron capture, or the R process. Free neutrons bombard lighter elements, building them up into heavyweight champions like platinum, uranium, and yes, the gold in your wedding ring. In just seconds, a single merger can produce hundreds of Earth masses worth of precious metals, scattering them across interstellar space in glowing, radioactive clouds. The evidence is written in starlight. Astronomers studying the aftermath of a neutron star collision in 2017 detected the unmistakable fingerprints of heavy elements in the expanding debris. Spectroscopy revealed tellurium, cesium, and gold being flung outward at 1/5 the speed of light, like cosmic shrapnel from the ultimate smithy. Even more astonishing, the sheer abundance. Calculations suggest these rare events could account for half of all elements heavier than iron in the universe. That means the platinum in your catalytic converter, the uranium fueling nuclear reactors, even the iodine in your thyroid, all owe their existence to neutron stars that slammed together billions of years ago. But the implications go beyond bling. These mergers are cosmic recycling plants. The heavy elements they create become raw materials for new stars, planets, and even life. Earth's gold deposits, for instance, likely arrived via ancient meteorites enriched by neutron star debris. It's a humbling thought. The same forces that obliterate stars also seed the universe with the building blocks of complexity. Without these violent unions, planets might lack the heavy elements needed to form metallic cores, magnetic fields, or even radioactive elements that keep Earth's interior churning. What's wild is how often these events occur. While rare on human timescales, perhaps once every 100,000 years per galaxy, the universe's vastness means a neutron-star merger happens somewhere roughly every minute. Each one is a fleeting but prolific factory, its products drifting through space until gravity gathers them into future worlds, and when those worlds host life. The atoms forged in those cataclysms become part of us literally. The gold in your jewelry might have crossed half the universe before finding its way to your finger, a silent testament to the chaos that creates. So the next time you hold something heavy and precious, remember, you're touching stardust twice removed, first from the supernova that birthed the neutron stars, then from the collision that transmuted them into something rarer. The universe doesn't just build, it destroys to rebuild, turning the remnants of dead stars into the seeds of new beginnings. And in that endless cycle, even violence has its purpose, writing the elements of life across the cosmos one cataclysm at a time. Rising 50,000 light-years above and below the Milky Way's disk, stretching halfway to the edge of our galaxy, twin bubbles of searing gamma rays glow like ghostly hourglasses in the void. These are the Fermi Bubbles, colossal structures discovered just over a decade ago, and they're rewriting what we thought we knew about our galactic backyard. Imagine two geysers erupting from the galactic core, not with water, but with particles moving at nearly the speed of light, a testament to a cataclysmic event that rocked the Milky Way millions of years ago. The bubbles get their name from the Fermi Gamma Ray Space Telescope, which first spotted their faint glow in 2010. At first, astronomers thought they might be artifacts, glitches in the data. But the more they looked, the clearer it became. These were real, enormous, and brimming with energy. The edges of the bubbles crackle with gamma rays, the highest energy light in the universe, produced by cosmic rays slamming into interstellar gas. Inside, the space is eerily empty, a million-degree plasma, so hot it's blown a near-perfect vacuum in its wake. What could create such monstrous structures? Prime suspect sits right at the center of the Milky Way, Sagittarius, a star, our supermassive black hole. Though it's quiet, now barely flickering compared to active galactic nuclei, the Fermi Bubbles suggest it wasn't always so docile. One leading theory posits that around 3.5 million years ago, Sagittarius, a star, devoured something massive, perhaps a gas cloud or even a star, and the resulting explosion blasted these bubbles outward like a cosmic shockwave. The energy released would have been unimaginable, equivalent to 100,000 supernova detonating at once. But here's the twist: the Fermi Bubbles aren't just relics of past violence. They're actively shaping the galaxy around them. The same high-energy particles filling the bubbles are constantly leaking into the Milky Way's halo, seeding it with cosmic rays that may influence star formation far from the galactic center. Some scientists even speculate these rays could play a role in the mysterious missing baryon problem, the whereabouts of half the ordinary matter the universe should contain. What's truly humbling is realizing we might be living in the aftermath of a cataclysm we barely noticed. If the Fermi Bubbles formed when Sagittarius, a star, last awoke, early hominids were already walking the Earth. The light from that eruption would have washed over our planet long before human eyes could comprehend it. Today, we're left with these fading echoes, a reminder that even quiet galaxies like ours have tempestuous pasts, and that black holes don't just lurk in space. They sculpt it. The universe is supposed to be indifferent, no preferred direction, no cosmic North Star, no axis around which everything aligns. Yet when scientists mapped the afterglow of the Big Bang, they stumbled upon something that shouldn't exist, a bizarre alignment in the cosmic microwave background that points directly at our solar system. They called it the axis of evil, not because it's malevolent, but because it threatens one of cosmology's most sacred principles, the idea that the universe is uniform in all directions. This anomaly first emerged when researchers noticed strange patterns in the CMB's temperature fluctuations. Instead of being randomly scattered, like static on an old television, certain hot and cold spots seem to line up along a specific plane, one that bizarrely coincides with the ecliptic, the path our planets follow around the Sun. It's as if the universe left a fingerprint and it's pointing right at us. The odds of this happening by chance, less than 1 in 1,000. Either we're witnessing a statistical fluke of epic proportions, or there's a crack in our understanding of the cosmos. Some theorists argue this could be evidence of a pre-Big Bang structure, a relic of some deeper physics that imprinted itself on the early universe. Others suggest it might reveal hidden dimensions, warping space-time in ways we can't yet model. Then there's the unsettling possibility that it's not the universe that's special, it's us. Could some local effect, like the gravitational pull of nearby galaxy clusters, be bending light in ways that fake a cosmic alignment? Or worse, could it mean our observations are contaminated by something as mundane as dust in our own solar system? The truth is, no one knows. The axis of evil resists easy explanation, gnawing at the foundations of modern cosmology. If the universe truly has a preferred direction, it would upend the Copernican principle, the idea that Earth holds no special place in the cosmos. Suddenly, we'd have to grapple with the notion that our corner of existence might be unique, not just another speck in an indifferent void. That's a philosophical earthquake disguised as a data anomaly. For now, the axis of evil remains one of science's great unresolved riddles. Every new CMB map refines the measurements, but the signal won't vanish. It lingers, whispering that maybe, just maybe, we've missed something fundamental about how reality is stitched together. And until we solve it, this cosmic oddity serves as a reminder. The universe is under no obligation to make sense to us. Sometimes it throws a curveball just to see if we're paying attention. Somewhere in the direction of the constellation Eridana lies an emptiness so vast it defies comprehension, a cosmic desert where galaxies should thrive but don't. This is the Eridana Supervoid, a staggering billion light-year-wide bubble of near-nothingness that might hold the key to one of cosmology's most stubborn puzzles, the mysterious cold spot in the cosmic microwave background. While most of the CMB's temperature variations are tiny fractions of a degree, this particular chill is far deeper than standard models predict, as if a piece of the universe forgot to turn on the heat. At first glance, the cold spot seems like a glitch, a statistical anomaly in an otherwise smooth cosmic snapshot. But when astronomers traced its location, they found something eerie. It aligns almost perfectly with the supervoid, a region where galaxy clusters are suspiciously scarce. The connection isn't trivial. According to general relativity, light passing through a void should lose energy climbing out of its gravitational well, shifting to colder wavelengths, an effect called the integrated Sachs-Wolf effect. In theory, the supervoid could be casting a shadow on the CMB, imprinting that unexplained chill. Yet the numbers don't quite add up. the Eridana Supervoid, for all its emptiness, isn't vacant enough to account for the cold spot's intensity. Its gravitational pull should only cause a minor temperature dip, not the dramatic plunge we observe. This leaves scientists at a crossroads. Either the void is far stranger than we've measured, with hidden structures amplifying its effect, or the cold spot is evidence of something far more exotic, a collision with another universe, a flaw in spacetime's fabric, or even a relic of quantum fluctuations from before the Big Bang. The debate hinges on perspective. Some researchers argue the supervoid and cold spot are unrelated cosmic neighbors whose alignment is pure coincidence. Others propose the void might be part of a larger, undiscovered structure, its true scale still hidden from our telescopes. Then there's the radical idea that the cold spot isn't a shadow at all, but a bruise left by our universe brushing against another bubble in the multiverse. Each explanation pushes the boundaries of physics, challenging our understanding of how matter clusters, or fails to across the largest scales. What makes the Eridana Supervoid so compelling isn't just its size or its possible link to the CMB anomaly. It's the reminder that emptiness can be as revealing as abundance. In a universe obsessed with structure, filaments, clusters, walls of galaxies, this void stands as a counterpoint, a place where the rules of gravity and growth seem to pause. Whether it's the key to the cold spot or just another cosmic oddity, one thing is certain: sometimes what's missing speaks louder than what's there. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radio waves so powerful it made astronomer Jerry Amon scribble, "Wow." In the margin of the data printout, that single word gave the signal its name, but the mystery behind it has echoed through decades of scientific debate. The pattern was unmistakable: a narrow band transmission at precisely the frequency hydrogen emits naturally, a logical choice for any civilization trying to announce its presence across the cosmos. Yet despite countless searches, we've never heard it again. What makes the wow signal so tantalizing is what it wasn't. It wasn't static from a passing satellite, interference from earthly technology, or the murmur of a distant quasar. The signal's intensity spiked and faded exactly as you'd expect if it came from a fixed point in space, sweeping past the telescope's receiver as Earth rotated. The Big Ear Observatory's twin beams ruled out most natural explanations. Whatever sent it wasn't repeating, wasn't drifting, and wasn't from our solar system. For 72 seconds, the universe seemed to shout directly at us, then fell silent. Theories abound. Some suggest it was a comet's hydrogen cloud glowing at just the right frequency, though subsequent scans of the same region found nothing. Others propose an exotic astrophysical event, like a rogue pulsar or a previously unknown celestial phenomenon. Then there's the spine-tingling possibility that it was intentional, a deliberate beacon from a civilization far older than ours, flicked on just long enough to tease our curiosity. Imagine the sender's calculus: a brief, unmistakable ping, then silence, waiting to see if we'd call back. What's haunting is how the wow signal mirrors our own early attempts at interstellar communication. In 1974, just 3 years earlier, humanity beamed the Arecibo message toward a star cluster 25,000 light-years away, a one-time transmission never meant to be repeated. Could the wow signal be someone else's version of that same cosmic handshake? Or is it proof of how little we still understand about the radio sky's hidden orchestra? Every follow-up scan of that patch of space near the constellation Sagittarius has come up empty. Newer telescopes like the Allen Telescope Array have listened for echoes, but the silence persists. Yet the signal's legacy endures, a reminder that the universe is vast enough to hide countless surprises in its static. Maybe we'll never solve the riddle of that summer night in '77. But the fact that we're still listening, still wondering, tells its own story, one about a species unwilling to accept that we're alone in the dark. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1980s, they carried humanity's hopes into the unknown, but they also carried a mystery. As these trailblazing probes hurtled toward the edges of the solar system, something unexpected happened. Their speed didn't quite match predictions. An unknown force, equivalent to a billionth of Earth's gravity, was gently but persistently tugging them backward. This tiny discrepancy became known as the Pioneer Anomaly, a gravitational riddle that haunted physicists for decades. At first, the anomaly seemed almost trivial, a drift of just 9,000 kilometers per decade off course. But in the precise world of orbital mechanics, even microscopic deviations demand explanation. Was it the pull of unseen dark matter clumping near the solar system, a flaw in our understanding of gravity itself, or something as mundane as heat radiating unevenly from the probe's plutonium power sources? Each possibility carried weight. If dark matter was the culprit, it hinted at hidden structures lurking in our cosmic backyard. If gravity behaved differently at extreme distances, it could upend Einstein's theory of general relativity. But the simplest answer, thermal radiation, proved the most elusive to confirm. Here's why Pioneer's design was uniquely vulnerable to subtle pressure from its own heat. Unlike later missions like Voyager, which stabilized with spinning thrusters, Pioneer relied on directional radio antennas that inadvertently turned the spacecraft into tiny photon engines. Every watt of heat radiating from its power system could, in theory, produce enough recoil to account for the anomaly. Yet modeling this effect was maddeningly complex. Even the way warmth bounced off internal components or leaked through insulation panels might skew the numbers. It wasn't until 2012, after years of reconstructing decades-old engineering data, that a team finally pinpointed thermal radiation as the primary cause. But the story doesn't end there. Some researchers still argue the thermal explanation doesn't fully close the case. Could there be deeper physics at play, masked by the probe's design quirks? The debate lingers because the implications are so profound. If even a fraction of the anomaly stemmed from new gravitational effects, it might hint at exotic theories like modified Newtonian dynamics, an alternative to dark matter that tweaks how gravity operates at cosmic scales. Others speculate about the gravitational influence of undiscovered planets or primordial black holes drifting unseen beyond Neptune. What makes the Pioneer Anomaly timeless isn't just the scientific detective work it inspired. It's the humility it imposed. These probes, built with 1970s technology, revealed how much we still don't know about the forces shaping our own solar system. They reminded us that exploration doesn't just answer questions, it uncovers new ones hidden in the noise of the data. And sometimes the universe's quietest whispers lead to its loudest revelations. Far beyond Neptune's icy orbit, where sunlight fades to a dim twilight, the Kuiper belt stretches like a frozen archive of the solar system's infancy. This vast ring of icy debris, home to Pluto and countless dwarf planets, should gradually thin out as you move farther from the Sun. But something strange happens about 50 astronomical units out an abrupt boundary astronomers call the Kuiper Cliff, where the population of objects drops off a cosmic precipice. It's as if someone drew a line in the celestial sand and declared, "No trespassing for space rocks." This sudden edge defies our expectations. In most models of planetary formation, the outer solar system's debris field should taper off gently over hundreds of astronomical units, not vanish within a narrow zone. One compelling explanation points to gravitational interference, perhaps from an unseen planet massive enough to sweep its orbital neighborhood clean. The hypothetical planet 9, if it exists, could be the cosmic bouncer responsible for this sharp cutoff. Simulations show a distant super-Earth with an elongated orbit could shepherd Kuiper belt objects into clustered groups while leaving other regions eerily empty. Yet there's another possibility, one that reaches back to the solar system's birth. The Kuiper Cliff might mark the original outer edge of our protoplanetary disk, the swirling cloud of gas and dust that birthed the planets. Just as a chef's knife leaves clean cuts on dough, the young sun's radiation and nearby stellar nurseries could have trimmed the disk at this boundary, leaving no material to coalesce beyond this point. Supporting this theory, some exoplanet systems show similar sharp edges in their debris disks, suggesting this might be a common feature of planetary formation. What makes this frontier doubly fascinating is how it challenges our detection capabilities. The Kuiper Cliff lies at the very limit of where current telescopes can reliably spot small, dim objects. New observatories like the Vera Rubin telescope, set to begin sweeping the skies in the coming years, could finally settle the debate, either by finding the hypothetical planet sculpting this boundary or by revealing whether the cliff is truly as empty as it appears. Every faint speck of light detected beyond 50 carries implications, potentially rewriting our understanding of how planetary systems take shape. The Kuiper Cliff isn't just a curiosity, it's a time capsule from an era when the solar system was still finding its shape. Whether carved by a hidden world or frozen in place since creation, this boundary reminds us that even in our own cosmic backyard, mysteries lurk in the twilight. And like all great frontiers, it dares us to look deeper, to question our assumptions, and to remember that sometimes the most telling clues aren't in what we find, but in what's conspicuously missing. Beyond the Kuiper belt's sharp edge lies an even more distant and mysterious realm, the Oort Cloud, a vast spherical shell of icy remnants stretching nearly halfway to the nearest star. Unlike the flat, pizza-shaped disk of the inner solar system, this region is more like a hollowed-out snow globe, with trillions of frozen objects orbiting in all directions. These aren't just space rocks, they're pristine time capsules, preserving the original ingredients of our solar system in deep freeze for over 4.5 billion years. What makes the Oort Cloud so extraordinary is its isolation. While planets and asteroids have been baked by sunlight, bombarded by impacts, and chemically altered over eons, these distant wanderers have remained virtually untouched since their formation. They're cosmic refrigerators, keeping volatile compounds like carbon monoxide, methane, and even prebiotic molecules locked in ice at temperatures near absolute zero. When one gets knocked inward by a passing star's gravity, it transforms into the spectacular long-period comets that streak across our skies, glowing messengers from the solar system's birth. Take Comet Hale-Bopp, which lit up night skies in 1997. Its brilliant tail revealed traces of organic molecules and heavy water, a rare form of hydrogen with an extra neutron that matched predictions about the Oort Cloud's primordial composition. Unlike short-period comets from the Kuiper belt, which get recycled and altered by repeated solar encounters, these long-distance travelers deliver pure, unprocessed samples of the early solar system's chemistry. It's like comparing a well-worn paperback to a freshly printed manuscript. One bears the marks of time, while the other remains startlingly original. Yet for all its importance, the Oort Cloud remains stubbornly invisible to telescopes. Its objects are too small, too dark, and too far away to detect directly. Instead, we infer its existence from the paths of incoming comets, tracing their orbits backward to this distant point of origin. The numbers are staggering. Estimates suggest the cloud could contain more than 1 trillion icy bodies, with a combined mass several times that of Earth. Some may even be interstellar interlopers, captured from other star systems during the Sun's infancy, fossils of a time when our newborn solar system brushed shoulders with its stellar siblings. The real magic happens when gravity stirs this frozen reservoir. A passing star, a rogue planet, or even the Milky Way's tidal pull can dislodge an Oort Cloud object, sending it tumbling toward the inner solar system. As it approaches the Sun, heat vaporizes its ices, releasing gases and dust that form the iconic comet tails we admire. But hidden in that glow are clues to our own origins. The same water that fills our oceans, the same carbon that forms our DNA, all delivered by cometary impacts over billions of years. This leads to a profound thought. The Oort Cloud isn't just a relic, it's an active participant in Earth's story. The same process that sends comets our way may have once seeded our planet with the building blocks of life. And while most of these icy wanderers will never visit the inner solar system, their very existence hints at the delicate balance that makes our cosmic neighborhood unique. In the grand design of the universe, even the most distant and frozen places can hold the keys to understanding everything. Imagine Earth not just as a rock teeming with life, but as a vast, interconnected system that actively maintains the conditions for its own survival. This is the Gaia Hypothesis, a radical idea that redefines our planet as more than a habitat, but as a self-regulating superorganism. Named after the Greek goddess of Earth, the theory proposes that living organisms don't just adapt to their environment. They collectively shape it, fine-tuning everything from atmospheric composition to ocean salinity in a delicate dance of feedback loops. It's as if the biosphere itself has a built-in thermostat, one that's been adjusting the dials for billions of years. Take Earth's oxygen levels as an example. For over 2 billion years, photosynthetic bacteria have pumped oxygen into the atmosphere, while other organisms like those that decompose dead matter balance the equation by consuming it. The result, a remarkably stable oxygen concentration of around 21%, perfect for sustaining complex life. If this balance tipped even slightly, wildfires would rage uncontrollably or multicellular organisms would suffocate. Similarly, ocean algae release sulfur compounds that seed cloud formation, which in turn regulates global temperatures by reflecting sunlight. Even the humble lichen, slowly breaking down rocks, plays a role in sequestering carbon dioxide over geological timescales. What makes Gaia so provocative is its implication. Life isn't just a passenger on Earth, it's the pilot. When volcanoes spew carbon dioxide, plants flourish and absorb the excess. When temperatures rise, more clouds form to cool the surface. These aren't random acts, they're part of a system that resists chaos, correcting deviations like a tightrope walker adjusting their balance. Scientists call this homeostasis, and Earth's version has kept the planet habitable through asteroid impacts, ice ages, and solar flares that would have rendered other worlds sterile. Now zoom out to the cosmic scale. If life can engineer stability on Earth, could the same principle apply across the universe? Exoplanet hunters are starting to consider this possibility. On worlds where plate tectonics or stellar radiation should make climates erratic, might life itself be the unseen force maintaining equilibrium? We've already glimpsed hints. Mars' ancient river valleys suggest it once had a thicker atmosphere, possibly nurtured by early microbes. Venus, now a hellscape, might have been temperate before a runaway greenhouse effect overwhelmed its regulatory systems. the difference between a living world and a dead one could come down to whether biology learned to tame the chaos. This raises an even wilder question. Could intelligence be the universe's ultimate regulatory mechanism? Civilizations that master climate control, asteroid deflection, or even star lifting might not just survive, they could become cosmic gardeners, consciously maintaining their planets the way Earth's biosphere does unconsciously. Imagine a future where humanity stabilizes Earth's climate not just for our sake, but as part of a galactic tradition, a shared imperative among intelligent species to keep their cradles alive. Of course, Gaia remains controversial. Critics argue it assigns agency where none exists, that feedback loops are just chemistry and physics, not proof of a living planet. Yet even skeptics admit Earth systems display an uncanny resilience, one that defies simple chance. Whether by design or accident, our world has a knack for preserving the conditions that let life thrive. And if that's not a cosmic mechanism, what is? The Gaia Hypothesis does more than redefine Earth. It reframes our search for alien life. We're not just hunting for water or oxygen anymore. We're looking for worlds that behave like they're alive. Worlds where the air, oceans, and rocks whisper in a language of balance. Because if life can sculpt a planet, then the universe might be full of worlds that don't just harbor life, but are alive in ways we're only beginning to understand. Imagine tossing a book into a fireplace. The pages blacken, the words vanish, but the ashes still contain traces of its structure. Now picture that book falling into a black hole. According to Einstein's general relativity, every detail, every chapter, every ink molecule is crushed beyond recovery at the singularity. But quantum mechanics insists information can never truly be destroyed. This contradiction is the black hole information paradox, a battle between two pillars of physics that's raged for decades, and its resolution might rewrite our understanding of reality itself. The conflict starts with Hawking radiation. In the 1970s, Stephen Hawking showed black holes aren't completely black. They slowly leak particles, evaporating over eons. But here's the catch. This radiation appears random, carrying no trace of what fell in. If a black hole evaporates entirely, all the information it swallowed, whether encyclopedias or alien love poems, seems lost forever. Quantum mechanics revolts at this idea. In the quantum world, information is sacred. You should, in theory, be able to reverse time, tracking every particle's path backward like rewinding a film. Black holes, it seems, break the projector. Desperate to reconcile these views, physicists proposed radical solutions. One idea: firewalls. Just inside a black hole's event horizon, there might lurk a searing wall of energy that vaporizes infalling matter, scrambling its information into Hawking radiation. It's like a cosmic shredder, ensuring data escapes but at a horrific cost. Firewalls violate Einstein's principle that falling into a black hole should feel uneventful until tidal forces rip you apart. They also raise a chilling question. Is the event horizon a peaceful boundary, or a lethal holographic screen projecting our universe's information like a 3D movie? This hologram concept is where things get truly mind-bending. If the holographic principle is correct, black holes might not destroy information at all. They could encode it on their surfaces. Picture a black hole's event horizon as a pixelated sphere where every Planck-sized area stores one bit of quantum information. As matter falls in, its data gets smeared across this surface like ink on a balloon, later emitted via Hawking radiation in scrambled form. The information isn't lost, it's transformed, hidden in correlations between particles so subtle we've yet to crack the code. But the most tantalizing clue came in 2019, when physicists calculated that black holes might have quantum hair, tiny, invisible distortions in their gravitational fields that preserve information about what fell inside. Think of it like a cosmic fingerprint, subtle imprints left on spacetime itself. If true, it means black holes aren't the perfect vacuums Einstein envisioned. They're messy, complex systems with memory, their histories etched into their very fabric. Why does this matter beyond theoretical physics? Because the paradox isn't just about black holes, it's a stress test for the universe's rulebook. Solving it could reveal how spacetime emerges from quantum bits, how gravity marries quantum mechanics, even whether reality is fundamentally pixelated. Some theories suggest the paradox hints at extra dimensions or a hidden layer of physics that only reveals itself in nature's most extreme environments. Others speculate it's proof that our universe is a simulation, with black holes acting as cosmic garbage collectors compressing data to save memory. Every proposed solution peels back another layer of mystery, but the core lesson remains: black holes aren't just cosmic vacuum cleaners. They're laboratories for the universe's deepest laws, places where the ordinary rules break down and new physics flickers into view. And as we inch closer to resolving the paradox, we're not just saving information from oblivion, we're uncovering the operating system of reality itself. What if everything you know, every memory, every sensation, even the universe itself isn't real? Not in the way we think, at least. This unsettling possibility lies at the heart of the Boltzmann Brain, a thought experiment so bizarre it makes simulated realities and brain-in vat theories seem almost mundane. Named after 19th century physicist Ludwig Boltzmann, the idea springs from a simple question. In an infinite universe where particles randomly arrange themselves over unimaginable timescales, what's stopping a fully formed, self-aware brain from spontaneously assembling out of the void? Picture this: atoms jostling in the cosmic dark, collating by pure chance into the exact configuration of a human brain, complete with fabricated memories of a past that never happened, senses that perceive a world that doesn't exist, and consciousness convinced of its own reality. According to statistical mechanics, given enough time, even the most improbable events become inevitable. In a cosmos that's existed for nearly 14 billion years, or worse, in a hypothetical multiverse stretching eternally, such a fluke isn't just possible. Some calculations suggest it's vastly more likely than the gradual evolution of beings like us through conventional means. This leads to a paradox that keeps physicists awake at night. If self-aware entities can randomly fluctuate into existence, shouldn't the universe be teeming with Boltzmann brains rather than biologically evolved minds? After all, assembling a single conscious moment requires far less energy and time than crafting an entire universe's worth of stars, planets, and evolutionary history. The math seems to suggest that in the grand lottery of existence, isolated brains floating in the void should outnumber us by an unimaginable margin. So why does reality feel so stable? Some theorists argue this absurd conclusion exposes flaws in our assumptions, perhaps about the nature of time, the boundaries of quantum mechanics, or even the very idea of an infinite, eternal universe. Others propose that the existence of ordered structures like galaxies and living organisms implies an underlying mechanism suppressing Boltzmann brains, like an undiscovered law of physics that prevents such chaotic fluctuations. Then there's the spine-chilling interpretation that we might actually be Boltzmann brains right now, destined to dissolve back into chaos the moment our illusory coherence unravels. But here's where the thought experiment transcends philosophy and collides with cutting-edge cosmology. The Boltzmann brain paradox forces us to confront how little we truly grasp about consciousness, probability, and the fabric of reality. It's a cosmic mirror held up to our theories, revealing cracks in everything from quantum field theory to inflationary cosmology. If the math predicts that solipsistic hallucinations should dominate the universe, yet we observe a coherent, shared reality, what does that say about the models we've built our understanding upon? Perhaps the most profound takeaway isn't about brains at all, it's about the nature of observation. The mere fact that we're here to ponder this question might be the strongest evidence against Boltzmann brains. After all, if random fluctuations were the norm, why would we find ourselves embedded in a universe with such intricate consistency? The stars above, the laws of physics, the fossil record, all seem to suggest a reality far more durable and structured than a fleeting quantum hiccup. Unless, of course, that's exactly what the illusion wants us to think. In the end, the Boltzmann brain isn't just a quirky puzzle. It's a stress test for our deepest theories, a reminder that the universe's grand design might hold surprises we've yet to imagine. Whether a cautionary tale or a cosmic red herring, it challenges us to ask, how do we know what's real? And in a universe of infinite possibilities, what does it even mean to exist? What if the universe isn't the ultimate reality, but someone else's advanced computer simulation? The simulation hypothesis isn't science fiction anymore. It's a serious debate among physicists, philosophers, and even tech billionaires. At its core lies a provocative question. Could the quirks of quantum mechanics, the finite speed of light, even the pixel-like nature of spacetime, be clues that we're living in an artificial construct? Think of it as cosmic déjà vu, a nagging sense that the universe's rulebook feels a little too programmed. Start with quantum indeterminacy. Before measurement, particles exist in fuzzy superpositions, like a computer waiting to render a texture only when you look. This lazy loading mirrors how video games optimize processing power, generating details on demand to save resources. Then there's the universe's apparent resolution limit, Planck length and Planck time, scales so tiny that measuring smaller distances would require infinite energy. It's as if reality hits a hard-coded pixel density, the smallest units a cosmic GPU can process. Even the speed of light could be a built-in refresh rate, preventing the simulation from overloading as objects move too fast. But the most compelling case comes from mathematics. Our universe runs on elegant, computable laws, equations so precise we can predict eclipses millennia in advance or discover particles purely through math. In a natural universe, wouldn't we expect more chaos, more exceptions? Instead, reality behaves like optimized code, with symmetries and conserved quantities acting like error-checking algorithms. Some theorists argue that the very existence of mathematical structure hints at an underlying architecture, a programmer's blueprint for how things should interact. Of course, the hypothesis has critics. If we're in a simulation, where's the evidence of shortcuts or bugs? Proponents point to potential glitches, like the Mandela effect, where large groups misremember events identically, or quantum entanglement's spooky action, which defies classical logic. Others suggest cosmic rays could be background processes leaking through, like overhearing a server fan in a virtual world. Then there's the Fermi paradox's eerie silence. If the universe should teem with life, why do we hear nothing? Perhaps because extraterrestrials are non-player characters, or the simulation's boundaries are smaller than we think. The simulation argument also reframes existential questions. If consciousness is just lines of code, does free will exist, or are we following predetermined scripts? Could suffering be a necessary parameter to make the simulation feel real? And if higher dimensional beings are running this cosmic program, what's their purpose? Some suggest ancestor simulations, future civilizations recreating history, while others imagine we're entertainment or an alien school project. Yet for all its intrigue, the hypothesis has one glaring flaw: it's unfalsifiable. Without a way to peek behind the cosmic curtain, we can't prove or disprove it, but that doesn't render it meaningless. Like the Boltzmann Brain, it's a lens for examining our assumptions about reality. If nothing else, it humbles us. Whether we're stardust or strings of binary, the universe remains a mystery, one we're compelled to explore, even if the answers rewrite everything we thought we knew. The concept of a single universe feels almost quaint when you consider the staggering possibility that ours might be just one page in an infinite cosmic library. This is the multiverse theory, the idea that our universe isn't alone but one of countless others, each with its own unique set of physical laws, constants, and perhaps even dimensions. Imagine a vast cosmic foam where every bubble is a self-contained universe, some brimming with stars and life, others collapsing instantly or frozen in sterile emptiness. Our universe, with its finely tuned constants that allow for galaxies, chemistry, and consciousness, might simply be the rare bubble where everything lined up just right, a cosmic Goldilocks zone in a sea of failed experiments. The multiverse isn't just speculative fiction, it's a natural extension of inflationary cosmology. If the inflationary period that shaped our early universe never truly ended, but instead continues eternally in other regions of spacetime, then new universes could be constantly budding off like branches on an endless tree. Each one would inherit slightly different properties from the quantum fluctuations that birthed it, leading to wild variations in physics. Some might have stronger gravity, making stars burn out in seconds, while others could lack electromagnetism entirely, rendering matter inert and lifeless. In this scenario, the multiverse isn't an accident, it's an inevitable byproduct of the laws that govern reality at their most fundamental level. What's mesmerizing is how this reshapes the mystery of our universe's fine-tuning. The gravitational constant, the mass of an electron, the strength of the nuclear forces, if these values were even slightly different, life as we know it would be impossible. Traditionally, this precision seemed like a cosmic coincidence begging for explanation. But in a multiverse, it's no longer miraculous, it's statistical. With infinite variations, even the most improbable outcomes must occur somewhere. We find ourselves in a universe that works because, well, we couldn't exist in one that doesn't. It's like winning a lottery where the prize is reality itself. Yet the multiverse isn't just a philosophical escape hatch, it leaves fingerprints we might detect. Some theories suggest collisions between neighboring bubble universes could imprint ring-like patterns on the cosmic microwave background, like bruises from a long-ago cosmic bump. Others propose that dark energy's mysterious value might reflect our bubble's local physics rather than a universal constant. Even the elusive Planck satellite data, which hinted at anomalies in the CMB's polarization, sparked brief excitement as a possible multiverse signal before settling into ambiguity. But the most profound implication isn't observational, it's existential. If the multiverse is real, then every possible version of history is unfolding somewhere. Universes where dinosaurs never went extinct, where the Roman Empire colonized Mars, or where you made different life choices all exist in parallel, separated by unbridgeable distances in a higher dimensional landscape. This isn't just about alternate physics, it's about alternate stories, each as real as our own. The multiverse doesn't just expand space, it expands the very idea of reality, turning the cosmos into a kaleidoscope of possibilities. Of course, skepticism remains. Without direct evidence, the multiverse risks becoming a metaphysical curiosity rather than testable science. Critics argue it's a convenient way to dodge hard questions about why our universe is the way it is, pushing the mystery into an unobservable beyond. Even some proponents admit it may forever lie outside empirical proof, like a shadow cast by a reality we can never touch. Yet the multiverse endures because it solves puzzles nothing else can. It explains fine-tuning without invoking design, accounts for quantum probabilities by realizing all outcomes occur, and even offers a framework for string theory's notoriously elusive predictions. Whether a true description of reality or a beautiful metaphor, it forces us to confront the deepest question of all. In a cosmos of infinite variations, what does it mean to be here now in this particular universe, and why does it feel like home? The answer, if there is one, might lie not in the vastness of the multiverse, but in our own fragile ability to marvel at it. After all, a universe that gives rise to minds capable of imagining its alternatives is already a miracle, whether it's alone or not. From dark matter's hidden scaffolding to the quantum whispers that birthed galaxies, we've journeyed through a cosmos far more intricate than our ancestors ever dreamed. These 25 cosmic mechanisms aren't just curiosities, they're the hidden gears turning behind the curtain of reality, each one revealing how deeply interconnected existence truly is. The dance of supermassive black holes regulating star formation, the ghostly neutrino oscillations rewriting physics, even the chilling possibility that spacetime itself might be a hologram, all point to a universe that thrives on mystery. What's astonishing isn't just the scale of these phenomena, but how they shape our everyday lives. The gold in your jewelry was forged in neutron star collisions. The oxygen you breathe exists in perfect balance because Earth's biosphere learned to tune its own atmosphere. Even right now, trillions of dark matter particles stream through your body, holding galaxies together while leaving no trace. We're not just observers of this grand design, we're woven into its fabric, our very atoms stitched from stardust and cosmic violence. Yet for every answer science uncovers, a dozen new questions emerge. The axis of evil's eerie alignment, the Fermi Bubbles' silent roar, the haunting silence where the wow signal once flared, these aren't roadblocks, but invitations to look deeper. The universe doesn't surrender its secrets easily, and that's what makes the pursuit so thrilling. Each discovery peels back another layer, revealing not just how the cosmos works, but how little we truly understand. So the next time you step outside under a starry sky, try this. Let your eyes linger on any patch of darkness. In that void could lie undiscovered dimensions, parallel universes, or forces we've yet to name. The greatest lesson these cosmic mechanisms teach is humility, not just about our place in the universe, but about the boundless creativity of reality itself. Whether we're decoding black hole paradoxes or chasing magnetic monopoles through theoretical landscapes, one truth remains constant. The cosmos is always stranger, always richer than we imagine. Our journey through space and time doesn't end here. New telescopes probe deeper into the cosmic web. Quantum computers simulate conditions near the Big Bang, and experiments hunt for actions in the quietest corners of reality. Who knows what revelations tomorrow may bring? One thing's certain: the universe isn't done surprising us, and neither are we. So stay curious, keep questioning, and remember, every mystery solved is just the prelude to a grander one waiting in the wings. After all, the greatest story ever told is still being written, and we all get to be part of it.